All right, let's finish up the last couple of problems in chapter 18, starting with question 16. We're told iron 3 oxide can be reduced by carbon monoxide in the following reaction. Use the following thermodynamic data at 298 K to determine the equilibrium constant at this temperature. And again, we're given delta H, delta G, and S values. So the thing that's sort of the giveaway of the equation that we need to use in this problem is the fact that we're told we're looking for the equilibrium constant. Okay, and remember that's K. So the equation that we need is a new equation we haven't seen in this problem set yet, but it's that negative RT ln of K, that's equal to delta G. So we have a reaction here. We can go ahead and calculate what the delta G of the reaction is. Again, that's going to be products minus reactants. So we have 2 moles of iron, but iron's delta G is 0. All right, we've got 3 moles of carbon dioxide, 3 times negative 394.4 kilojoules per mole. All right, so those are my products minus my reactants. Fe2O3, that delta G is negative 742.2 kilojoules per mole. And then for carbon monoxide, we have 3 moles of negative 137.2 kilojoules per mole. All right, so we can go ahead and quickly calculate what delta G is for this reaction. I'll pause and give you guys a couple of seconds to do this. All right, so the value of delta G for the reaction, negative 29.4. All right, so we've got this value of delta G. We can plug that in on the left-hand side of our equation, and now we can just solve for what the K is in this reaction. So negative 29.4 kilojoules per mole is equal to negative R, and R is 8.314 joules per mole Kelvin. So we need to make sure these energy units again are consistent. So I just divide my R by 1,000, so 0.008314 kilojoules per mole Kelvin times T, natural log of K. Okay, so the T that we're given in this equation is 298 Kelvin. So now we can do this division. 29.4 kilojoules per mole will be divided by negative 0.008314 kilojoules per mole dot Kelvin times 298 Kelvin, and that's equal to the natural log of K. So now we should evaluate what the left-hand side is in this equation. Okay, and so what I found is 11.866 is equal to the natural log of K. Now remember, to get rid of the natural log, I need to do E on both sides. So I use my exponential function on both sides. The exponential and the natural log cancel out. So e to the power of 11.866, that's going to be my answer. And that is 1.42 times 10 to the 5th. All right, and that is now equal to K. So that is answer D for number 16. All right, number 17, we have another reaction. This time we're given a standard Gibbs energy value, and we're given some partial pressures, and we're asked to find delta G. So if we have a standard Gibbs energy value, and we're asked to find delta G, then that means we're going to be using this equation. Delta G is equal to delta G standard plus RT ln of Q. All right, and remember our Q in this reaction means products over reactants, and we have these two partial pressures. So Q would be equal to 0.10 divided by 100. All right, or 0.0010. Now, all we have to do is we just have to plug in what the value of delta G standard is and the temperature of 298 Kelvin. All right, so delta G is equal to positive 209.2 kilojoules plus my R, which, as we mentioned in the previous problem, needs to be in kilojoules per mole Kelvin. So we divide 8.314 by 1,000 times T, 25 degrees Celsius in the problem, is 298 Kelvin times the natural log of 0.0010. So now this is just a straight plug and chug problem. I'll give you a couple of seconds just to calculate this. All right, so after doing these calculations, you should get 192.08 kilojoules, and that would be answer C. So now we go on to number 18. Given the following thermochemical equations, calculate delta G for the following reaction. All right, so this is a lot like a process you learned about in chapter 5, where you could sort of combine multiple pieces or multiple reactions together to build a new target reaction. So we call that Hess's law. And so the idea is I can manipulate both of these equations at the top here. I need to sort of somehow think about how to manipulate these to build this. And the way that I sort of think about it, right, is I'm looking for each of these individual components in this reaction and trying to find the one reaction up here where those components show up. So for instance, in the reaction that I'm looking to make, I have 2 moles of N2O as a reactant. If I go up to these two equations for which I know delta G for, the 2 moles of N2O show up on my top reaction. Notice N2O does not show up at all on this bottom reaction. So that just means I need to use the top reaction, but to get it to be a reactant, I have to flip the direction that this arrow is pointing. So I can flip the direction of this reaction, which just means now my N2O is a reactant, my O2 is a reactant, and my NO becomes a product. All right, and that delta G now flips its sign to positive 139.6 kilojoules. All right, I need in my my target reaction down here, I need NO2 on the product side. Okay, so NO2, notice NO2 only shows up in this bottom reaction, but it has a coefficient in that bottom reaction of a 2, and I need to get it to be a 4. So I can do that, right? The thing that I can do is I can multiply every coefficient in this equation by 2. And if I do that, I need to multiply my delta G value by 2 as well. So I'll go ahead and rewrite this as 4 moles of NO plus 2 moles of O2 yields 4 moles of NO2. All right, now the delta G here, the sign is not flipped, but I do need to multiply this by 2, so 2 times negative 69.7. Okay, so now what we can do is we can see a couple of things are going to cancel out. My NOs cancel out. My O2s can be added together, but what I'm left with is 2NO2 plus 3O2 yields 4NO2. So that's my target reaction that I was looking for. So the delta G for this reaction would be 139.6 positive plus 2 times negative 69.7. All right, so that delta G value would be equal to 0.2 kilojoules. All right, so that would be answer A. Okay, number 19, the combustion of glucose is given by the following reaction. It's very exothermic. The conversion of ADP to ATP is given by the following reaction, which is positive. All right, so notice I have a really exothermic reaction, have positive delta G for ADP to ATP. Which of the following statements is most correct? Glucose combustion is coupled to the non-spontaneous conversion of ADP to ATP. Okay, glucose combustion is coupled to the non-spontaneous conversion of ATP to ADP, or both glucose combustion and ADP are spontaneous, or ADP is necessary to drive the glucose combustion. All right, so sort of when we are trying to work through these questions, again, the thing to recognize is I have this negative sign for my top reaction, which means this is spontaneous. All right, and a positive sign for the second reaction, which means this is non-spontaneous. All right, so the idea is we can convert ADP to ATP. That can happen inside of our body, but that reaction by itself is non-spontaneous. What has to happen is this reaction is coupled to all of this energy that we release by the conversion or combustion of glucose. So I can convert a lot of ADP to ATP from all of this energy. So in the old days, delta G was known as the Gibbs free energy. And what that free term means is if you had a negative value here, this is the amount of energy that's free to be used by other processes. Okay, so if we come back down to our choices here, glucose combustion is coupled to the non-spontaneous conversion of ADP to ATP. That would be the correct answer because ADP is being converted to ATP in our second equation. So it's definitely not this one. Both of these are definitely not spontaneous because delta G in our second reaction is positive, and ADP is necessary to drive glucose. That's wrong. Glucose combustion is necessary to drive ADP conversion. All right, so choice A would be the right answer here. All right, last set of questions. Just talking about entropy increases its value in the universe. This is just again to get you to think about the fact that the second law of thermodynamics says entropy of the universe is always increasing for spontaneous reactions. If you talk, you exhale gas particles. That entropy then in the surroundings of your mouth, that entropy goes up. Entropy of the universe goes up. So that would be a true statement.